So for the rest of these, I'm just going to sort of graph them in pieces and do a quick explanation rather than having the video walk through the entire process. So here we're converting these fifth powers to third powers just because same shape but easier to graph because the outputs don't get as big as fast. So I started by graphing the parent function and I numbered my axes by 2 here. So I'm counting by 2s here. So 2, 4, 6, 8. And by 1s along the x, so 1, 2, 3, 4. So it looks a little squashed, but it's not. It's just the numbering that makes it appear that way. And then I'm interpreting this as a shift to the left 1 and up 2. So the graph's going to look like this, shifted left 1 up 2, because again we're counting by 2s along the y. So it appears to be left 1 up 1, but it's actually left 1 up 2. So this is the g of x function is in red. So for number 3, again, this was a 6th power polynomial. I changed it to a 4th power, a quartic, and obviously the same for the g of x function. So I went ahead and graphed the parent function. Again, I counted by 1s along the x, but 4s along the y, so I just happened to label every other one. So this is actually a 1, 1, negative 1, 1, 2, 16, negative 2, 16. So it looks like a quartic with a vertical shrink, but it's just the way that I numbered the axes. And that's just so I could fit more of the picture on this graph, or on this coordinate plane. And then interpreting these transformations, we have a vertical stretch by 5, a reflection in the x-axis, and a shift to the right 2. So when you apply those transformations, you get this red graph. This is g of x. So we have right 2, reflection in the x, so it's opening down instead of up, and vertically stretched by 5. So I took this point that was over 1, up 1, and I went over 1, down. 1 times 5 is 5. So 1, 2, 3, 4, 5. Same over here, and I can't fit any other points on this graph, so I'm just going to have to leave it with those 3. So for number 4, already a cubic, which is nice and easy. I went ahead and I graphed the parent function, but I sort of slid the x-axis up a little bit. I can't see as much of this behavior, but I see more of this, and I know this guy's going to be a shift down 4, so I figured this will kind of give us space to show that. So in interpreting these transformations, this is a horizontal stretch by 2. I could actually simplify this and cube it and make it 1/8 x cubed minus 4. And now that would be a vertical shrink by a factor of 8. And I could graph that instead if I wanted to, but based on the way it's written, it's a horizontal stretch by 2, and I'll show you how to do that. And then we have down 4. So order of operations, we do this first. We do the horizontal stretch by 2 first. So that means that, and I've, just to be clear, I've got a 1-to-1 ratio on my axes here. So 1, 2, 1, 2, so we don't have to be as careful with the distortion. So horizontal stretch by 2 says points on the y-axis don't move, but those that are already away from the y-axis are going to move twice as far away now. So this is over 1, now it's over 2. This is over 1, now it's over 2. This stays put. This was over 2, now it's over 4. But now I need to take each of these points and shift them down 4. So I'm going to go down 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and this is going to go down 4, which I'm not going to be able to fit. And now when I finish graphing this, this is what my function looks like. So normally if I were to sort of look at it this way, another way to interpret this is I'd normally go out 1, up 1, out 2, up 8, because 2 cubed is 8, but 1/8 of that would be up 1. So that sort of was achieved anyway, even though I interpreted it as a horizontal stretch by 2. So this is the resulting function g of x. So I'm just going to go through the rest of these guys pretty quickly. Here I graphed the parent function of a quartic, and I counted by 4s along the y-axis, just by 1s along the x-axis. So the parent function's here. Here's the g of x function, which is really just a vertical shrink by a factor of 1/8, because if I raise a negative x to the 4th power, it's positive x. In other words, a reflection in the y-axis for something that's already got y-axis symmetry is going to look identical. And what I did to graph the shrink is normally I go over 2 up 16. Now I go up an eighth of that, which is 2. Since I'm counting by 4s, that's half a space. I don't usually fit the 3's on the parent function because 3 to the 4th is 81. That's huge. But since I'm now dividing it by 8, that's roughly 10. And 10 when I'm counting by 4s is roughly 2.5, or is exactly 2.5. So that's what those points represent. I went ahead and I skipped question number 6 because it's pretty redundant. It looks an awful lot like question number 2. Here we're writing rules, which means write the function. For number 8 and 9, we don't have to graph them, we just need to write them. So here's my f of x function right here.